Hello, everybody, and welcome to this webinar of the Siderwin project. I am José Ignacio Barbero from Tecnalia, and I think you can see some of the other partners of the project. Tecnalia is a partner of the Siderwin project, and we are also involved in different technical issues and in the managing the dissemination activities. Tecnalia is a research center in Spain, and I will be the chairman of this webinar. I have a master's degree on mechanical engineering, and I am currently project manager of the steel industry projects. We develop projects in Tecnalia to increase efficiency and productivity of steelmaking processes, and also to improve the quality and properties of steel processes. This So in this webinar, this will be the different presentation that I guess you already know. But before we go to this presentation, some comments about this webinar. We will record the webinar, and later we will make it available, so you will receive a link to this webinar when it is ready. All the attendees, you have the microphone muted, but you can communicate to us through the chat. So any questions or any comments you may have, please write it in the chat, and we will try to answer them. After each presentation, we will have some time for questions, and also at the end of the webinar, we will have some time for more questions. So before we start the webinar, just a brief introduction to the Siderwin project. Siderwin is a European project under the SPIRE program. The title is Development of New Methodologies for Industrial CO2-Free Steel Production by Electrowinning. And the aim of the project is to develop a breakthrough innovation compared to the conventional steel production route by electrowinning iron from its natural occurring oxides at low temperature and in an aqueous-based electrolyte. So the idea is from the iron oxide to put in the middle the electrolysis process, and later on go with the iron to the melting one. So we can thank you for your participation in the webinar, and the first presentation. Sorry. The first presentation will be the green of steel, non-zero steel making for the EU Green Steel Deal, Green Deal, Siderwin. And we have the pleasure and the honor to have as a speaker to Pierre Birat. Pierre is one of the pioneers of these new technologies for the steel making. And right now, he's a consultant and owner and manager of the Steelman company, who works on environment issues, energy, and materials. He studied in France and in California, and he was the Secretary General for the STEP European Steel Technology Platform after working many years in research for ArcelorMittal. Pierre is a world expert on net zero technologies and an experience stemming from his tenure as director of the UCOS program a few years ago. And he's also the author of Rosen books, Sustainable Material Science, Environmental Metallurgy, published in 2 volumes in these last 2 years, 2020 and 2021. And also the content of this book, he teaches it at the University of Science and Technology of Beijing. He's also one of the organizers of the Society and Materials conferences, SAM. The 15th of this conference took place this year online. So Hervé, whenever you want, you can go ahead. Oh, Pierre, sorry. Pierre, you are muted. Pierre. No, we cannot listen to you, Pierre. Está como Hervé, ¿eh? Okay, sorry, I think we have some technical problems with the microphone of Jean-Pierre that is from the Hervé computer.
Okay, it should work now.
Yes, yes, it is working now. Okay.
Okay, I'm sorry about this. So thank you, José, for this very nice introduction. So I'm really about to spend 10 minutes with you people, continuing the introduction to the webinar. I want to put the webinar and the Siderwin technology in perspective. And in order to do this, I will go through a number of steps. So I will start by explaining what is the European Union Green Deal, because really Siderwin is really the answer, one of the answers to the Green Deal as far as steel is concerned. I will explain then what are the net zero pathways which are open for making steel. And I will then focus on the fact that there are two solutions among those routes, those production routes I would have presented, that are based on electricity. One is using hydrogen for direct reduction, but the hydrogen is produced by electrolysis of water. And then there is electrolysis, direct electrolysis of iron ore, which is the technology that will be discussed in our seminar today. And then I will finish up by reintroducing the content of the seminar in the kind of interesting language that Hervé Lavelaine proposed. Okay, so this should move on. Okay, so what is the European Green Deal? Well, the European Green Deal is, oh my God, I want to go back. How do I go back? Okay, yeah, the European Green Deal is a very ambitious policy which was put forward by the European Commission 2 years ago. And this policy talks about everything. You see, it's a very complicated picture, but I want to point out what it's on the left in the middle, which says achieving climate neutrality. So really what the Commission says as it sets as its first target objective is to stop having any CO2 greenhouse gas emission by 2050. And so what they want is what they call, what we all call now net zero solutions. And this applies to every stakeholder, every industry in the European community, but also it should apply to the steel industry. And what was interesting was the fact that within weeks of the publication of the Green Deal in Brussels, all the steel stakeholders said, well, we'll do it. We will manage to become a net zero producer by 2050. Of course, there are other things which are also important, but not today. Okay. So the second point is trying to explain what are the net zero pathways which are open for steel production. And as you know, there are two major ways to make steel. And one way is to use an integrated steel mill, and the other way is to use an electric arc furnace steel mill. So either start from iron ore or start from scrap. Well, there is not enough scrap to make all the steel that the society needs today. So the integrated steel mill are still leading the way. They are the most important in terms of production today, and this will continue for a while. So in order to find net zero solution for the integrated steel mill, there are really, again, four ways to go. One means keep using carbon as a reducing agent. So let's keep using blast furnaces, but then this will create CO2. So we have to capture the CO2 and to store it, or maybe to use it to transform it into some chemicals. So this can be done in the blast furnace, since we use a blast furnace, but it can also be done with all the smelting reduction reactors, like the Haizana smelter, which is being run at TRL 607 in IJmuiden at Tata Steel. The second route, which is open for starting, for replacing the integrated steel mill, is to use green hydrogen instead of carbon. And if we have hydrogen, of course, there is no more greenhouse gas emission, but we need to ensure that the hydrogen is produced by using green electricity, and this green electricity should do the electrolysis of water. And the third way is to use electricity directly without going through the intermediary step of producing hydrogen. And this is a direct electrolysis of iron ore, which is exactly what we will be listening about today. Siderwin and a couple more endeavors somewhere else in the world. And the fourth way to avoid emission is to use biomass carbon. And so we use carbon, but carbon which is in the cycle of life, and in such a way that there is no net CO2 emissions again. Okay, so this will take care of the upstream part of the integrated steel mill. There is some downstream part which is not so well identified, but again, there are two solutions there. One is to use electricity. The other one is to use hydrogen even in the reheating furnaces. And now if we look at the second route to make steel, electric arc furnace steel making, well, the solution is fairly simple, because we only need to use green electricity, and by 2050, the electricity grid in Europe will be green. Okay, so among the routes, the two routes I just showed you, there are two which focus on electricity, hydrogen, direct reduction, and electrolysis. Well, I want to explain to you what is foreseen for the electricity use in the future by 2050. And of course, there are all kinds of scenarios. There will be a very interesting one presented toward the end of this seminar. But I referred to published information, and the IEA, the International Energy Agency, came up with a roadmap for global energy for the world, and to reach net zero by 2050, and therefore to reach 1.5 degree temperature increase, which is exactly the commitment of the Paris meeting. So how do they see the future in this scenario? They see, of course, in 2050, the GDP of the world will have doubled. We'll have 2 billion more people on the earth, but we will use 8% less energy than today. Now, by that time, 2/3 of this energy will come from renewables, and therefore hydro, geothermal, bioenergy, solar, and wind. Solar will be the largest part, they say, which means that it will have to increase 20 times compared to the level it has today, and wind will come next, and it will have to increase by 11 times. So at the end of this period, 2050, 50% of the energy used will be available as electricity, which is increasing the electrification of the economy by 2.5 times compared to today. And by then, we will have 90% of electricity directly from rent, and 75% of all the energy needs. And of course, the cars will adapt, and the homes, and sea and air transport. Okay, so now let's just give the floor to the people who are actually working, who are really trying to change the deal, to trying to come up with a solution that can actually make it possible to reach a very ambitious target set by the European Commission. And we will have 4 presentations. The presentation, they are trying to answer some questions which are fairly provocative and which were raised by Hervé Lavelaine. So the first question is, can we really produce iron from iron ore by using electricity? So what are we talking about here? Is it real? Yes, well, we'll see what they have to say, but we know the answer already, of course. The second question is, now that we have seen some people showing us that the reaction happens in the laboratory, can it be scaled up to a size which looks a little bit more like what the steel people are used to, which looks more like an industrial process? And so this is the second question. Can you really scale it up? The third question is, now assuming that Siderwin really calls for so much electricity, we can imagine from what we know that the amount of electricity needed will be tremendous compared, for example, to what the steel sector uses today. I mean, how can the utilities, how can the electricity companies react to that? How can they manage to provide this electricity to the steel sector based on, for example, 100% Siderwin? And how can they manage to balance the grid? So again, you will have some quite interesting answers. And then the final presentation will be a kind of summary of everything. And is it, can we really, truly use Siderwin as a solution to reach the challenge of the EU Green Deal? Can we get net zero steel production from Siderwin? Okay, that's all I have to say. Thank you so much. José, you have the floor again.
Okay, thank you very much, Jean-Pierre, for your presentation and the introduction to the Siderwin project webinar. And the first presentation now will be Sevasti Koutsoupa. Is electrodecomposition of iron oxide a feasible reaction? Well, Sevasti is graduated in 2018 from the National Technical University of Athens. She's holding a master's degree in mining and metallurgy, and since then she has been working as a junior researcher and at the Technologies for Sustainable Metallurgy group of the NTUA. She focuses on electrochemistry techniques applied on industrial byproducts to achieve a more environmental friendly metal production. So, Sevasti, whenever you want.
Thank you, Mr. Barbero, for the introduction. And good afternoon to all. On this session, I'm going to explain you if the chemical process of Siderwin, meaning the iron oxide electrodecomposition, is feasible. First, I will explain how all started and some information about the theoretical background of the process and how the Siderwin team reassured its feasibility with some results. Finally, I will introduce some cases of alternative raw materials that could be used to make the process more eco-friendly than already is. So, to start with, what is electrodecomposition in general? Is a type of chemical reaction when an electric current is passed through the aqueous solution of a compound. To be more specific, is a process by which a tiny coating of metal can be deposited into a conductor by electrolysis of a solution containing a chemical complex. In our case, the desired metal ion that needs to reduce is the iron cation in hematite. While the iron oxide is decomposed, oxygen and hydrogen is produced. But under what condition is this reaction really feasible? To investigate the feasibility of every electrolytic process, a Courbet diagram is essential. It is also known as a potential pH diagram and is a plot of the possible thermodynamically stable phases of an aqueous electrochemical system. Concerning the Pourbet diagram for iron oxide, it seems that the production of metallic iron is feasible under acid and alkaline conditions from minus 0.55 volts versus standard hydrogen electrode. The alkaline system has the important advantage of avoiding the multivalencies of iron with the presence only of the divalent iron cation. So, the Siderwin process combined the previous knowledge with a know-how of alkaline water electrolysis, plus the conventional electrowinning of metals, and formed the production of iron through alkaline electrolysis at low temperatures. An alkaline electrolyte has chosen the 50% sodium hydroxide, low temperatures as 110 Celsius degrees applied, and finely ground hematite was used as the raw material. The overall reactions now that take place during electrolysis of iron oxide is the iron oxide reduction and the oxygen evolution, but the systems seems to be more complex than that. The hematite dissolution in alkaline media that is shown at the diagram on the right is quite low. More specific, for 18 molar sodium hydroxide at 100 Celsius degrees, it has found out around 2 ppm of iron is diluted in the solution. That means that the production of metallic iron is not produced only from the reduction of divalent iron. That resulted this type of electrolysis is not a typical electrodecomposition process and follows a different route. The mechanism of the cathodic reduction of hematite seems to follow a solid-state reduction mechanism. To be more precise, first, the divalent cations that are diluted in the solution reacts with the hematite particles, producing magnetite. At the same time, the iron deposition of dissolved iron or ions takes place at low rate. After that, the iron oxide particles are absorbed to the cathode, and the magnetite reacts with the metallic iron and the hydroxide ions, resulting in the increase of the divalent iron ions in the electrolyte. So, the reduction of divalent ions from the iron oxide dissolution plus the magnetite reaction with iron that is previously deposited on the cathode resulted in the production of metallic iron. It is impossible to have this high rate of production without the contact of the particles with the cathode. During the last years, a lot of experiments took place and reconfirmed that the iron oxide reduction at lab scale is a feasible process. The experiments conducted with 50% sodium hydroxide, as I referred earlier, and temperatures around 110 Celsius degrees. Also, the solid particles size was 10 micrometers. The anodes was from nickel, and different type of cathodes has tested as stainless steel and carbon. The applied current density was 1000 ampere per square meter, and all the experiments gave high Faraday efficiencies, higher than 90%, and the cathodic iron grew as a solid-state deposit. On the left picture, you can see the electrolytic cell of our partners in NTNU, and next to it is a hematite pellet that was used as a cathode that has reducted almost fully to metallic iron. On the right pictures, you can observe the dendrites of the iron deposit from our partners in University of Aveiro. Okay, Siderwin project, except of dealing with the pure iron oxide reduction, has explored and some alternative raw materials to investigate if there is a byproduct that can be used as a feed. Bauxite residue is a rich byproduct in iron oxide, containing around 40% of it. This material resulted from alumina production during Bayer process, and its valorization is very important towards the environmental crisis. In NTUA, we have extensively tested bauxite residue as a possible raw material for Siderwin process, and you can see more details about the experimental procedure in our video on Siderwin YouTube channel. Comparing the two raw materials, the pure hematite and the bauxite residue, we resulted that these two materials are very different. Bauxite residue achieved 70% current efficiency at 110 Celsius degrees, but for higher current densities, the bauxite residue Faraday yield reduced at 36%, when hematite yield is 90% and more. While researching the temperature effect, applying the bauxite residue's more efficient current density, hematite seems to result higher efficiencies in lower temperatures than bauxite residue, which at lower temperatures the efficiency decreases intensively. So the pure iron ore still results higher Faraday yields at higher current densities, and bauxite residue electrolysis needs optimization to reach an increased current efficiency by applying higher currents to the system. These are some images from the scanning electron microscope showing the deposition from pure hematite from experiments that was under 138 Ampere per square meter. The metallic iron deposition seems to be thick and tightly connected to the electrode surface. To compare the two raw materials, also the bauxite residues deposition studied with the scanning electron microscope, and unlike the hematite deposition, the bauxite residues metallic iron is not as strongly connected with the electrode surface. The right image is showing that there are a lot of gaps between the deposition and the stainless steel cathode. These observations leads to the conclusions that the two raw materials mechanisms differ a lot. There are strong indications that the non-homogeneous distribution of the electroactive species, meaning the impurities that Br contains, results lower current densities. The coverage of the cathode surface with the iron oxide particles is reduced compared to the pure hematite, and thus the current efficiency decreases in this alternative raw material case. Another alternative raw material that is very attractive for the Siderwin process is mild scales. Mild scale is produced by rolling red-hot iron or steel billets in rolling mills. It contains high percentages of iron oxide, with the hematite to be the predominant, and also metallic iron. A few experiments have shown that this material is promising for the Siderwin process, achieving high current efficiencies such as 97%. To sum up, the electrowinning of Siderwin process is considered as a solid-state electrolysis at high alkaline solution. The alternative raw material study is under investigation with different materials to compete as a possible feed for the electrolytic process, even though the mechanism seems to differ. The byproducts use of other metallurgies could offer to Siderwin process an extra role, and that is the exploitation of waste. Of course, the electrodecomposition of iron oxide in alkaline environment at low temperature is a feasible reaction in lab scale, which is characterized of the high current density at 1100 Ampere per square meters, high Faraday efficiency 91.4%, low temperatures 110 Celsius degrees, low voltage 1.6 volt, high energy efficiency 3.6 megawatt hour per ton of iron produced, and has the possibility of alternative material use. All these features leads this technique to industrial scalability. Thank you very much.
Okay, thank you, Sevasti. I think we have some time for questions before we go to the next presentation. So the first will be, what about the purity of the iron product? What is the percentage of metallic iron produced by iron ore or by alternative raw materials?
Yes, the purity for the iron ore and for the alternative raw materials is bigger than 90%. It's around 90 to 95%. And the other phases, except of metallic iron, is magnetite.
Okay, and the next one will be, do all type of iron ore can be treated by Siderwin?
Yes, but the most treated are the hematite-based ones.
Okay, wait a minute. There is another one. Let me check if I can. Wait.
Bueno, pregunte las suyas.
No, ¿dónde está? Wait a minute. Okay, so we can move to the next presentation. So we have seen now that the Siderwin process is feasible on a laboratory scale. So, but it is possible to apply on pilot scale. This issue will be addressed by the next presentation. That is the electrolysis of primary steel production scalable and industrialisable? This presentation is going to be presented by Thierry Conte. Cedric will not be able to be with us today. So Thierry is a fluid mechanical engineer and founder of CFD-Numerics in 2008. CFD-Numerics is specialized in CFD for different sectors and industries such as energy, aeronautics, automotive, medical, steel process, metal production, and so on. So Thierry, whenever you want. Es que no está hablando. Thierry. Thierry.
Thank you, José, for the introduction. I wasn't able to unmute my microphone. Okay, good afternoon, everyone. I will here present, after the two previous presentations, how we managed to move from a lab experiment for iron electrolysis to industrial pilot. So just to remind you how we came up to the Siderwin pilot. Then we start from the laboratory setup as described by Sevasti from NTUA. Then there were some first experiments on an electrowinning cell that was called Ulcowin that were able to produce 4 kilograms of iron in this cell. And then the idea of the Siderwin project is to go further and to be able to build a pilot project to build 100 kilograms of iron, and this is the objective of this project. So the main idea was to move from a TRL4 to a TRL6 during this project. So as you can see here, in a lab experiment, we are able, of course, to produce iron at a lab scale below than 100 grams. During the Ulcowin project with the prototype, they were able to create an iron plate up to 4 kilograms. And then, as you can see on the right, the idea was to build a pilot cell to generate an iron plate of 100 kilograms. So one of the important part of the project was to achieve this pilot cell to be able to generate such an iron plate of 100 kilograms. So before building this pilot, we have decided to rely on CFD simulations to define the optimal cell, as there were many challenges to address regarding all the flows in the cells, flows of electrolyte and flows of bubbles as well. So just to give you a quick overview of the CFD process. So the main challenge of the project regarding the CFD approach was to find the right cell design to be able to remove a very large amount of oxygen bubbles that are going to be generated by the electrolysis process. In fact, as we want to create a 100 kilogram iron plate, this production will produce a lot of oxygen bubble that will have to be managed. In fact, what we want to avoid, what is a major issue, the potential major issue, is to get a lot of oxygen bubble accumulation in the cell. And if those bubbles are running in the cell everywhere, they can go to the cathode and lead to a very dramatic loss of efficiency. So to avoid this kind of problem, we have decided to design the cell using CFD simulations. Just a reminder, CFD is an acronym for computational fluid dynamics, which is in fact the numerical simulation of the flow. So the flow can be a flow of water, a flow of electrolyte, a flow of gas, and so on. And more specifically to Siderwin, we have to focus on two-phase flows modeling. I mean, we have to describe very accurately by simulation how the flow of oxygen bubbles and of electrolyte are running in the cell, to understand how it works, to analyze these flows, and then to optimize the designs of the cell. So the project regarding CFD modeling was split in two parts. The first part was to develop the method of the CFD model. In fact, modeling numerically with 3D simulation the flows of electrolyte and bubbles is not an easy task. And then we had to develop a very relevant methodology to calculate those two-phase flows. And then once this methodology has been validated, we move to the optimization design process to define the Siderwin cell. And then we have used those CFD models for many topics, for many equipments in the cell. But the main application of CFD model was to determine the cell angle, because as I will show you, the cell is not horizontal, but is very close to the vertical position. So we had to define those cell angles. We had also to define the anode design, because as I will show you, it's not an easy task, and we can't use what is currently used for electrowinning. So the anode and the cell angle are two important topics. And then we had also to design some other equipment in the cell. The first one is a degassing device, because just above the anode, we will have a mix of bubbles and of electrolyte, and that has to be properly separated. We also have some hydraulic issues in the cell itself to optimize the inlet distributor, the outlet collector, to reduce the pressure drop of the cell, and to specify the pump. All these aspects has to be addressed so as to get a very efficient cell. Quickly on the oxygen bubbles management. On the left side of the cell, you have a very rough scheme of the conventional electrowinning process, where you have an electrolyte between two electrodes with some bubbles generated close to the wall, which are going up. And this kind of electrolyzer is not applicable anymore to Siderwin, as we have to deal with a very huge amount of bubbles, as we have to reduce the size between the distance between the cathode and the anode. And then we have to think to a very new design to be able to deal with the gas in the cell. And that's why we have decided to rely on CFD simulation to perform very efficient optimization of the cell. So I've listed some challenges that we had to address during the project. We wanted to keep a cell design with a very short distance between anode and cathode to optimize the electrolysis efficiency. As I will show you, we had to deal with counterflows of electrolyte and bubbles that could create some troubles in terms of bubbles accumulation. What we wanted to avoid is accumulation of bubbles close to the cathode that could lead to very dramatic loss of efficiency. We wanted also to take advantage of what is called a gas leaf effect. In fact, when bubbles are going up out of the cell, some electrolyte will be on train. This is a force that we can use to make the cell more efficient. And finally, we have to design some devices to perform a really efficient gas electrolyte separation and then send back the pure electrolyte to the cell. So just to give you an idea right now of the design installation, as you can see on the left, from this design installation, CFD models will focus on the cell itself, which is in the red square here. And then we did the optimization of the cell using the models to manufacture an efficient cell, as you can see on the right. So just to explain quickly how the flows are running in the cell, you have to imagine that the cell is more vertical than horizontal, but it was just a way to illustrate the flows here. You can see that we have the main electrolyte, which is going in the cell from the pump. This electrolyte is running in the cell itself here, where there is an anode, which is just above the cathode, which is at this level here, if you can see with my mouse. And then the cathode is here. And when the current is running through the cell, some iron is going to deposit on the cathode, and some bubbles will be generated on the anode. And because of buoyancy effect, because of gravity, the bubbles will flow up out of the cell. And while they are flowing up to the outlet of the cell, some electrolyte will be entrained by the bubbles. So here in this area, we have a flow of mixing of bubbles and electrolyte that we need to separate in this area so that we can send the bubbles out of the domain and get back the electrolyte and send it back to the main flow. So this is a kind of loop for the electrolyte that allows an efficient electrolysis of the electrolyte. So to go back to the objective of those CFD simulations, of course, as for many CFD simulations, we wanted to reduce the pressure drop. We wanted to minimize the efficiency loss because of friction, because of pressure drop in the cell. We wanted also to define the best shape for the electrolytic inlet. I mean, what we wanted to get is a very smooth and uniform flow entering the anode. One of the main objectives was to determine the optimal cell angle. So we have decided to put an angle in the cell to enhance the buoyancy effect of the bubbles and to remove the bubbles from the domain. We had also to determine a very optimal design for the anode, so as to avoid some bubbles accumulation in the anode. And finally, we had to define the optimal separation device in this area to be able to properly separate the gas and the electrolyte in the cell. So in the next two slides, I will just show you that we were able to address those issues, and we made some maybe three main achievements using CFD. What you can see here is that we were able to propose a design that avoids oxygen bubbles to move everywhere in the cell. And we were able to avoid accumulation of bubble in the cell while keeping a very short distance between the anode and the cathode. We were also able to deal with the electrolysis gas counterflows. We were able to take advantage of the gas leaf effect and to properly deal with the electrolysis gas counterflows. It was the second achievement. And then the third achievement was to properly remove the gas from the electrolyte in this degassing device on the top of the cell. As you can see on the picture, which is representing the oxygen concentration in the cell. We start here in the electrolyte with an oxygen concentration close to 0. We have generation of bubbles in the anode here. And then the mix of electrolyte and gas is coming up. We have the separation. And then here in this area, we have only pure oxygen that could be removed from the cell. So we, at the end of this process of iterative process between buildings and between CFD simulations, we were able to define what we think to be a very efficient cell. So now we were ready to move to the industrialization. So this was performed by people from John Cockerill. As you can see here, they were able, using CFD simulation for the pilot, but with their experience, to design an industrial pilot, as you can see here on the picture. So this pilot was designed with experiments with experience, from previous project, from the simulation, for all the simulations we did during this project. And then we were able, as you can see here, to build the pilot itself with an upscaling factor from Ulkowin to Siderwin of 30, with a high level of instrumentation. And we were able also to define all the equipments that are needed for such an exploitation of the cell. I mean, we had to define the supply for the continuous iron ore supply, the device and the equipment for the gas collection, something which is important because, as you have already seen, at the end of the electrowinning process, we get an iron plate, which is deposited on the cathode, and that need to be harvested safely. So we had to define a harvesting system to remove the iron plate from the cell. And we also have to take in account the footprint of such a process. So the pilot has a big vertical extension, so that in the future we should be able to stack different cells to limit the footprint of the equipment. What we are going to test in the near future with the exploitation of the pilot is to test what has already been presented. It means the electrification of a primary steel production with a pilot which is very flexible regarding energy input, which is able to participate in the demand side response electricity network, and something important, which is able to deal with interruption of production to be able to stop the pilot and then restart him depending on some electricity constraints. We are going also to test the possibility to use some other iron oxide sources, as already mentioned by Sevasti in the previous presentation. And then we will test the proposed pilot to a fully electrified primary production, and seeing the radical improvement in terms of energy efficiency. So as a conclusion, in this process, we are at this step here. So all the previous studies has been completed, the design is completed, and the supply as well. The erection and commissioning are at the end of the process, and we will start the exploitation of the system. Then after Siderwin, we have to think about further upscaling. We have to think of the optimization of the footprint, because it's a very important task. And think of how we can even better optimize the design to get a very efficient process. So I thank you for your attention. If you have any questions, please feel free to ask. And I think that we can share a short video showing the building of the pilot in ArcelorMittal's facilities in Mézières-les-Messes. As you can see here, so you can see the installation of all the equipment, of the tanks, of the hydraulic piping, of the iron supply, of the cell itself, and of the harvesting system. So thank you again for your attention, and if you have any questions, feel free to ask.
Yes, there are a few questions. Can wait to finish the video. Okay, so there were some questions. The first one would be, do you couple electrochemical calculation with the flow bubble calculation in the CFD model?
In the first validation we did, in the first validation step, we did couple the simulation by calculating the current density and then deriving the terms of bubble production close to the anode. And when we had to go to a very, very large model, we assume a constant bubble rate. But it's something that we can simulate. It's just a question of the size of the model and the time you have to perform the entire simulation.
Okay, then there was a question to clarify. I think it was in slide 50 or 51. There was a picture showing 4 kilograms per 100 kilogram. What does this relate to?
I can answer the question. For the 4 kilo sample was produced by an intermediate pilot and named Ulcowin, and developed during the Ulcos project. And now with Siderwin, our objective is to change of scale by a factor 30, and which relates to this 100 kilo sample that are expected to be produced in the Siderwin pilot.
Okay, another question for the cell is, which is the working temperature?
110 degrees.
Mm-hmm. And there was another one, which is the material of the anode?
It's made in nickel, pure nickel. Huh? It's very similar to water electrolysis.
Mm-hmm. Another question, could the oxygen be a valuable byproduct?
Oxygen has a low commercial value, but it has an environmental value that we are looking to improve and to improve its use, and it's an aspect that is related to the LCA environmental efficiency of the process that is addressed later in the webinar.
Okay, and maybe the final right now would be, what are the next steps in the development of the technology, and which are the major obstacles for further upscaling?
Siderwin is a very new route, and today the main obstacle is to find and to develop the partnership with supplier that provides the very specific equipments that we need, typically for anodes, for cathodes, for slurry handling, etc. And to my perspective, it seems that we need to develop this aspect to accelerate the industrialization.
Okay, there are many other questions, but maybe we are going to follow the webinar and we will try to answer more questions at the end. And anyway, any questions that we will not answer today, we will try to answer later, and we will either in the newsletter of the project or at the end when we publish the video. We are getting all the questions you are submitting now, and we will try to answer all of them either today or later on. So the next presentation is, thank you, Hervé and Thierry. So let's go to the next presentation, that is how decarbonizing primary steel production through electrolysis could play a role in the European power system. This will be presented by Matthildi Apostolou and Caroline Bono from EDF. A brief presentation of both of them. Well, Matthildi is a research engineer at EDF. Her expertise concerns a sectoral overview of the metallurgical industry with a transverse vision of hydrogen and industrial CO2 emissions. She currently conducts technical studies and technico-economic analysis for the identification of the decarbonization potential for diverse industrial segments. Matthildi holds a PhD in mechanical engineering and optimization from the École des Mines University in France. And Caroline Bono is a senior research engineer with more than 10 years experience in the energy and numerical simulation sectors. At EDF, she is involved in the assessment of renewable energy integration and the induced flexibility requirement. She is currently participating in several European projects on the modeling of the European power system with large shares of renewable energy alongside new solutions to address the different challenges that emerge. She holds a PhD in mechanical engineering and eccentric computing from the University of Michigan. So Matthildi and Caroline, whenever you want.
Perfect. Thank you very much, José Ignacio, for the introduction. We have some camera issues, so you will not be able to see our faces today. So in our presentation with Caroline, we will focus on the power system and the implementation of Siderwin on a European level, and the flexibility that is provided by the demand-side response. So we have simulated different perspective scenarios for a time horizon in 2050 in order to assess Siderwin's impact in terms of energy consumption on one hand, that is defining the evolution of the energy mix, and on the other hand, we have studied the costs and benefits for the power system in terms of the flexibility potential that can be offered by Siderwin, and also an evaluation of the carbon emissions reduction. So if we pass on the next slide, our presentation will be divided in two parts. we would like to take some time to explain our methodology and the tools that we have used in order for you to be able to understand the complexity of the problem and the different perimeters that we have defined. And then we will give you an insight on the main results of our study. So what you can see here is that we have adopted a three-step approach where we define a reference scenario where we describe the environment in 2050, and then we study different alternative scenarios in order to match supply and demand, and we evaluate in terms of costs and CO2 emissions the different energy mixes. So the parametric assessment requires a lot of input data to be defined. Firstly, the power system must be described in details in terms of energy mix and renewable energy profiles, CO2 emissions and costs. The steel industry must be also described in terms of localization of the steel plants and also volumes, so production of steel in 2050, and also the Siderwin profile, that is the different energy balances and also the demand side response profile. In order to ensure transparency and to be consistent with the European Union Commission's vision of the future, we have used the maximum of public data that you can see, for instance, the European reference scenario and the International Energy Agency data or a Eurofer data. And I would like to stress out that as far as the demand side response profile is concerned, we know that industrial processes that use electrolysis have a potential to provide flexibility for the system. So based on the analysis made by the University of Aveiro and their different experiments at the laboratory level, we're able to prove that up to 90% of Siderwin's power can be moduled or stopped, and this is the flexibility potential that we were able to investigate in our study. So if we pass to the next slide, how were we able to combine all this data? We have defined the reference scenario and studied different variables, but the main challenge was to take into account the additional demand that because taking into account this additional demand leads to changes in the generation fleet. So based on our hypothesis for the steel sector growth and the share between the primary and the secondary steel in 2050, and considering 100% substitution of blast furnaces in Europe in 2050 by Siderwin plants, we established a 471 terawatt hours additional electricity demand to be met in 2050, which corresponds approximately to 12% of the European electricity demand nowadays. In order to meet this demand, we have activated low carbon intensity generation sources, and we have proposed different scenarios. So in this presentation, we will focus on three scenarios. So in the orange boxes, you can see that we are proposing the additional demand to be met either by additional nuclear power, either by additional offshore wind power, and the medium scenario where we activate 50% of nuclear and 50% of offshore power. And of course, these scenarios take into account the renewable energy potential for each country, and also are consistent with the phase-out decisions of the different policies of the different state members. And we duplicate these three scenarios by activating the demand-side response possibility for the Siderwin plant. So we have a total of 7 scenarios that were studied. And to give you an example, in the right part of the presentation, we can see the evolution of the generation mix in Europe. And if we focus on the green part, we can see that initially, for instance, we have 8% of offshore wind, and we pass to approximately 17%. And if we focus on the purple part, which is the nuclear capacity, we pass from a share of 60% to 25% in the nuclear variant. So if we pass in the next slide, we will discuss on how this energy mix was obtained.
So yeah, so we performed numerical simulations so that we can assess the role that Siderwin and DSR could have in the power system. We use a state-of-the-art model that is a unit commitment model that works on an hourly basis. The first exercise that was done was without Siderwin, and we used scenarios that were based on the EU reference scenarios at the horizon of 2050, where we have 66% of renewable energy inside the mix. Those scenarios include the targets and the directives of the European Union. And to describe the scenarios, we are going to describe different countries. And so the countries are pictured on the map on this slide. And then in each country, we're going to be placing the production plants, and we're going to give a fairly detailed description of those plants. Once we have the mix per country, then we're going to put the interconnections between different countries. We're going to give also a macroeconomic context where we're going to have fuel prices, we're going to have CO2 prices, which are coming from the scenario description. And we also have the electricity demand. And because the electricity demand as well as the production of renewable energies depend on the weather, we don't only have one weather year, so we don't consider 2050 and we have only 1 year. We're going to have 50 different years about where we're going to have years where we have cool spells, years where we have heat waves, years where we have more or less hydro, where we have more or less wind, so that we can assess a different type of situation. And then we run the scenario through a unit commitment model, and this gives us different sets of results. We're going to have the production plans for each of the plants in Europe. We're also going to have the prices for the different countries, and we're going to have the usage between interconnections. So this is the first the first scenario, the first set that we have, and then we're going to be adding Siderwin on the next slide. So the Siderwin demand is added in the electricity demand. And then we are going to match this demand with carbon-free sources, as Matthildi explained. So we're going to have additional wind or additional nuclear or additional wind and nuclear. And this is adjusted in energy annually. And then once we have those, so the Siderwin demand and the additional production, we're going to have an investment loop that's going to adapt the power mix so that we can ensure that we have an adequacy between supply and demand at an hourly level. And so we do, for each scenario, we're going to do 2 passes, one with DSR and one without DSR. And I'm going to show you on the next slide the results. So here, the first slide, we look at the impact of DSR on the makeup of the power mix. And so here, as I said in the previous slide, we adapt the mix with gas plant. And what's interesting is that if you look on the far right, you're going to see that the installed gas capacity is going to change depending on the different mixes. And this is why it's very important to do the adequacy on an hourly basis. And you can see that the demand response has an impact on peaking plant capacity and is going to sharply reduce the need for peaking plants in Europe. And on the next slide, I'm going to give you an illustration of what happens during a DSR episode. So on this particular result, the system was dimensioned with DSR, so we have less capacity installed in gas. And this is a numerical experiment. So we look at when we have cutoffs. The cutoffs are very rare. They're less than 5% of the time. And here we extracted one episode so that we can understand how those cutoffs happens. So here the scenario is the scenario where we have 100% offshore wind to meet the additional Siderwin demand. The offshore wind on this graph is in teal. And what we can see is that we have between the 2 red bars an episode where we have very little wind production, And on the right of the last red bar, you can see that you have a much larger wind production. So what happens here is that the cutoff happens when the wind production is very little. And this is where Siderwin actually comes into play by allowing the supply and the demand to be matched on this particular episode. And as I said earlier, those episodes, I mean, we have the impression maybe that on this episode it happens, it's for a long period of time, but actually there are very few episodes that are like that, and we just extracted once so that you could get a chance to see what happened.
And so if we pass to the next slide, we wanted to synthesize the different results. So the first point that you have to keep in mind, and that our study has illustrated, is that the deep decarbonization of the steel industry that is enabled by Siderwin is not jeopardized by the impact on the power system. And by this, we mean that the additional demand of electricity related to 100% substitution of blast furnaces in Europe by Siderwin plants can be met by low carbon means, that is mixes integrating a more nuclear or offshore wind, or a combination of those two, and with no environmental impact. So specific CO2 emission factors stay actually the same between the different scenarios. And in the second slide, we would like to stress out the impact of the flexibility, which, as we have seen, is able to, so in the next slide, the flexibility offers a capacity of approximately 39 gigawatts, and it's able to allow the balance of the power system in different episodes. For instance, when we have a low wind production, as Caroline has described, and there is also an economic place in this contribution of the demand side response. As you can see, as you have seen, we're able to substitute peak load gas plants in our different modelizations. And so to finish with our presentation, I would like to stress out that we will continue to investigate the demand side response profile of Siderwin by different tests on the pilot plant, and also provide a market analysis of this flexibility done by our partner RICA. Thank you very much, and we're open to your questions.
Okay, thank you, Matthildi and Caroline. There are at least a couple of questions. One is, does the huge consumption of electricity by the steel industry compromise its availability for other consumers?
So it's an interesting question. I mean, if we place ourselves in 2050, where we look to decarbonize our economy in a large, as a whole, electricity is a vector that can allow decarbonizing not only the industrial sector, but also the residential, tertiary, or even the transportation sector. So what we have showed in our study is that the power system at the European level, in the numerical scenarization that we have made, is able to meet this additional demand.
Mm-hmm. Okay, maybe a solution for that question is in another question that is a comment. Let's say it says, given the lower cost of green electricity in areas with a strong solar and wind resources, such as North Africa, and given that iron ores are often imported into Europe from, let's say, Mauritania, shouldn't that reduction take place in Mauritania before iron is exported to Europe, instead of increasing the electricity demand in Europe?
This is a very interesting question. So in our study, we have considered that the steel plants will be localized where they are today. So we haven't evaluated, let's say, a potential optimization of the localization of the steel plants, which of course it makes sense, match the demand with the energy supply. That is, for instance, proposing the implementation of a steel plant somewhere with a huge potential of offshore wind or solar energy, and etc. I think European industry faces also this potential delocalization, which can be done in terms of lower energy costs or material costs. But in our study case, we considered that the steel plants are where they are today.
Okay. And I don't know if we have this figure. What are your assumptions for the electricity demand for Siderwin per ton of steel produced in 2050, for instance?
What is the specific energy consumption of Siderwin plants?
Yes, per ton of steel.
Yeah, yes, I can answer. It's 3.7 megawatt hour per ton of steel, of hot rolled coil.
Okay. So maybe we can, there are more questions, but as I said, we will try either to answer at the end, or otherwise we will try to answer later on after the webinar. So the next presentation is about the impact of the Siderwin. So does Siderwin contribute to deep decarbonization? This presentation is going to be done by Kounina from QUANTIS. Anna is a senior sustainability consultant working at QUANTIS since 2010. Anna serves as an LCA expert and project manager with small to large size companies in agro-food, heavy industries, apparel, building, packaging sector, as well as within European research projects to assess the environmental footprint of disruptive technologies. So Anna, you can go ahead.
Thanks a lot, José, for this nice introduction. So I'm glad to take over now and provide you a glimpse into the environmental footprint of the Siderwin technology, more specifically to answer the question whether the Siderwin technology contributes genuinely to deep decarbonization. So I would like to start with the global context of decarbonization, which we have heard about a little bit earlier, but it's important to remind the global stakes about this ongoing planetary journey engaging all sectors. So first of all, this nice infographic from the World Resources Institute shows us the contribution of iron and steel to global greenhouse gas emissions in 2016. So the sector represents 7.2% of global emissions and contributes mainly to CO2 emissions, while other greenhouse gases are, for instance, methane and nitrogen dinitrogen oxide. So yeah, let me change. So then we can then focus on Europe. And we can see on this graph that the illustrative emissions pathways to achieve a net zero target in Europe are represented here. So this EU net zero roadmap targets a 30% reduction in 2030 compared to 2018 and being close to neutrality by 2050. So within this brown industry category, the steel sector has its part to play and can follow this reduction pathway with the proper policies and technologies. As mentioned previously by Jean-Pierre Birat, these objectives are part of the European Green Deal. So then to lead this decarbonization change, Europe needs novel industrial processes and cleaner technologies to reduce costs and improve market readiness. We can see here that Europe represents 10% of steel produced globally in 2020. However, it can inspire other steel producing countries by developing innovative technologies to decarbonize its steel and thus be positioned as a leader in these breakthrough technologies. Let's now take a closer look at decarbonization options for the steel sector to carry on with this global perspective. So, as introduced earlier, there are currently several technologies under development to meet these European net zero target. So the Siderwin technology that we're presenting today, then the direct reduction of iron ore with carbon neutral hydrogen that has been also introduced earlier. Then we have this Hizarna process, reduction of ore using up to 50% of scrap. And finally, a more straightforward carbon capture and use based on the same technology that we're using today, except that the emissions would then be captured and reused or stored. So while it is important to have in mind the development of each of these technologies, the aim of this presentation is not to compare their environmental performance, but rather to provide a deeper insight into the Siderwin technology assets. First of all, some key innovations that allow Siderwin to decarbonize steel production. So the core innovation is obviously the electrolysis process to transform iron ore oxide into metal, thus eliminating the blast furnace. And then we have a series of other innovations that allow even further decarbonization. And these are, for instance, the use of induction furnace instead of the electric arc furnace. So this is an innovation that has actually come while working in the previous months that has been investigated and proven that the induction furnace can have actually a lower electricity consumption than the electric arc furnace. And we have then the elimination of certain carbon-intensive inputs, such as lime, for instance, that can be replaced by an alkaline leaching solution. And finally, the stop of use of other fossil fuels at other stages. So for instance, by the elimination of CO2 emissions, by the substitution of natural gas with induction heating at the final production stage. So we will present the carbon footprint results following the scopes that are defined by the GHG protocol. As a reminder, so scope 1 emissions are the direct emissions that take place during the process. Then scope 2 emissions are emissions that are indirect emissions related to the electricity consumption. And finally, we have also the scope 3 emissions that stems from the value chain and different additional inputs that are used during the process. So what is the potential in terms of Siderwin in terms of decarbonization for each of these categories? So for scope 1, by electrifying steel production, the Siderwin technology obviously reduces the direct emission of the steel sector, so the direct CO2 emissions. Then regarding scope 2, and this was very well presented previously by Matthildi and Caroline, so the ongoing decarbonization of the electricity sector in Europe will drive the emissions of electricity down. And finally, for scope 3 emissions, high carbon footprint inputs such as lime, as mentioned previously, will be replaced in the Siderwin technology, which allows this further decarbonization. So here is a simplified summary of the different stages of the Siderwin technology that corresponds to the system we studied for the environmental assessment, and that was also further explained previously. Then just a few details about how we perform this environmental assessment of the Siderwin technology. So we mainly used data provided by ArcelorMittal based on the upscaling of the process that we've been discussing today. We are currently reusing data that has been developed by EDF, especially to have these specific modeling of the future electricity mix in 2050. And then we complemented all the different stages of the model with a further literature review. And we input all these data in our LCA software CIMAPRO and complemented with LCA specific databases such as EcoInvent to come up with these LCA results. So we can now deep dive in the figures to better understand the decarbonization potential of Siderwin. First of all, here are the electricity mix scenarios that we considered so far in our model. So in 2020, we used an average electricity mix as it was last year in Europe. Then for 2050, we used an electricity mix that was modeled according to the EU roadmap scenario. And finally, we had another scenario for the 2050 mix, which was based on only renewable electricity, and this is a hypothetical scenario. And as we are in the process of complementing this analysis, we are also integrating the mixes, the mix modeled by EDF in our model. And we can finally see here the carbon footprint of Siderwin compared to the reference technology of blast furnace, basic oxygen furnace. So we can first observe that switching from the reference technology, which has a carbon intensity of 2 kilograms CO2 equivalent per kilogram, to Siderwin could allow a reduction of up to 80% for the carbon footprint. Secondly, we can see a switch in the scopes that contribute to the carbon footprint. So we have this switch from scope 1 to scope 2. For the reference technology, scope 1 emissions, so direct emissions, represent 65% of the footprint. And for the Siderwin routes in 2020, scope 2 emission would represent 68% of the footprint. Then we can see in the two 2050 scenarios that this share of scope 2 emissions can fall down to 53% and even be negligible in the case we would have a purely renewable electricity mix. So finally, we can see the influence of the electricity mix and how this is key to ensure the decarbonization potential of the Siderwin technology. And I wanted to show you then in more detail which stage of the process contributes to the Siderwin carbon footprint with the example of the Siderwin 2050 scenario. And this is what we can see here. So we can see the contribution of the different steps of the Siderwin steel production to the scope 3 and scope 2 carbon footprint. Scope 1 has a low contribution, and this is why we did not investigate it further in this graph. So we can see here very clearly that the electrowinning and furnace stages are the key contributors to both scope 3 and scope 2, and that they are the key hotspots of the carbon footprint. So finally, in a nutshell, here is a summary of the key takeaways of the potential of Siderwin in terms of steel decarbonization. So we saw that thanks to all its innovations, and if we can ensure, if a green electricity mix can be ensured in 2050, we can achieve a carbon footprint reduction potential of up to minus 80% per ton compared to the reference technology today. And thus, the Siderwin technology is a precious route and a key asset to ensure to support the European Green Deal and the Europe commitment towards these net zero trajectory towards 2050. And then just a few words on the next steps on our side. So the project is obviously ongoing, and there will be further improvements and refinements in our model. And these results will be then integrated by October next year, so October 2022. So the model will be complemented and refined, and we will then confirm these results. So many thanks for your attention, and I guess we have time for a few questions.
Yes, thank you, Anna. There are a few questions, at least a couple of them. Which is the main contributor in the steel value chain in scope 3?
Yeah, so yeah, we can see, so I can go just a few slides earlier. We can see these, so here in orange, we have these scope 3 emissions that are hard to reduce, and this is related to the fact that there is this incompressible part of iron ore extraction, then building the infrastructure for each of the technology, both the reference technology and the technology. And one of the contributors is actually either the production of the lime or the alkaline solution. And so, yeah, it can be reduced up to a certain level, but for sure we cannot totally reduce these Scope 3 emissions.
Okay, the next question will be, is carbon policy a threat to the steel industry activity in the future?
Well, this is a good question. So I guess this is a common challenge to all sectors, and given the emergency of the climate crisis, all sectors are challenged to innovate and to propose solutions to fit into this 2050 roadmap. So for sure, it can be seen as a great challenge. But well, our role here today, I think, is to turn this challenge in a great opportunity. So this direct electrification route can be a great opportunity for innovation, and also an opportunity for Europe to be to show its leadership in the development of these technologies.
Mm-hmm. Again, another specific question of slide 81. What is your assumption regarding the amount of alkaline solution needed per ton of steel produced? This is related to slide 81.
Yeah, so I don't have the number in the top of my head now. I don't know, Hervé, if you have these numbers available.
The alkaline solution is not consumed. It's just a medium for electrolytic flow of current, and it is although there is some fuel losses due to drag flows, etc. In these assumptions, we consider that it is conserved, essentially conserved during operation.
Okay, so thank you very much, Anna. We can move to the final conclusions that will be done by Hervé Lavelaine. Hervé is the coordinator of the Siderwin project, and he's a research engineer at ArcelorMittal. He started being involved in steel-related electrolytic processes, such as electrogalvanizing for car panels, and for the last 18 years, he addresses the question of the electrification of primary steel production to propose a process solution for carbon neutral steel. He has already been the coordinator of the Euro project under the RFCS program between 2010 and 2014. And as I said, he's right now the coordinator of the Siderwin project. One of the most significant results from the related studies is the discovery of the electrochemical decomposition iron oxide at apparent solid state that confers the iron a conspicuous advantage for electrification. Hervé holds an engineering diploma from NSIC and Nancy. So Hervé, wherever you want.
Thank you, José. Thank you for this nice introduction. Hello to everybody. I hope that all this presentation has been informative to all of you. As you understand, the Siderwin project is not completed. It has been running for 4 years now, and we have a year now to deliver the most important results, which is the operation of the pilot that you have seen. I thank you, the panelists, for the results that have been presented. And you can see that already we can have some partial and provisional conclusion about this project. Siderwin tries to address firstly the question of direct application of electricity to decompose iron oxide. Our methodology is based on science, and we are much in depth to our academic partner for the results, for the very fine studies at laboratory level. Today we have been able to devise an electrochemical route that is very specific to the properties of the iron element, and it is highly probable that there is no more direct and more efficient way to decompose iron oxide into iron metal and oxygen gas with direct application of electricity. During Siderwin projects these last few years, parallelly to the laboratory developments, we propose a breakthrough technology, and this innovation is derived from extensive application of CFD simulation. The results have provided a cell geometry that is original, that organize optimally the flow of current, the flow of iron oxide, and of course the flow of gas, which is the main phase, problematic phase. And it's a system that extracts the metal plate discontinuously. There have been some questions in the chat asking for how the iron is harvested. Typically, the cell operates during 2 days, night and days, and then it is stopped, and the plate is extracted from the cell in situ. Thanks to this simulation presented by Thierry, the Siderwin project proposed a technology that operates close to the physical limits. Our cell is scheduled to operate close to 1.7 volts, which is quite very low, very close to the thermodynamical limitations. In this project, you have seen that the electrification of primary steel production is not the simple substitution of coal by electricity. It's very important to design a process that can be integrated in the electrical grid, but also in all of the material networks to achieve an economical relevance. Electricity is indeed expensive compared to fossil fuel, and to address this challenge of economical efficiency, we design a processing route that is well integrated with these networks. Siderwin capitalize also on this operative temperature, and which is low, 110 degrees, compared to conventional processes that are operated at 1000 degrees. In order to be flexible, we have a system where we are not limited by problems of passivation, because our system depassivates, it breaks down the oxides. So we have a good, today, good laboratory result showing that we have a good potential to propose a big industrial process that is flexible. And finally, I would like to share some thoughts about what could be the future of the steel plants compatible with this imperative of CO2 reduction. Firstly, the decarbonization imposes a complete reinvention of the steel production. We need to extract the iron metal with electricity, but also all the operation has to be electrified, and it's not straightforward. It needs some efforts. Although with electricity, we can see that we can expect that we propose a lower impact activity, inconspicuous plants, lower footprint, and lower resource consumption. In the future, it is highly probable that the activity will be much more intense. We will be more tightly connected to iron sources, unconventional and other iron ore sources from other metallurgy. We have seen the studies on the bauxite residue, but we are also looking at non-ferrous metallurgy such as nickel. And it is an activity that will be more sensible to the priority of the surrounding environment, and that is expected to be well adapted to the European urban conditions. And that's our partial conclusion. I thank you, all of you, for your attention and for your interest for this development. And we are now open to your questions.
Okay, thank you everybody, and thank you, Hervé. There are a few questions. How does the Siderwin technology relate to plans by many steel corporations to use direct reduction with hydrogen? Is it more efficient?
We expect Siderwin to be more efficient because it's more direct. We don't need to build two plants. Hydrogen needs one plant for hydrogen and one plant for reduction. Here we apply electricity in one plant, so we expect to have a lower capital cost. Also, iron, I think Sevasti has well presented the fact that the iron is a good candidate for application of electricity. At the start of this development, iron with its multivalencies was considered as a complex elements to be treated by electrochemistry, and by the treatment of the iron oxide, this specific route in alkaline condition, we can achieve a good condition of the transfer of electricity into iron metal, and we expect with this property to be more energy efficient than the hydrogen route. But also the direct reduction by electricity as a TRL, a maturity, technological maturity, which is much lower than the hydrogen route, which capitalize on the DRI, the direct reduction iron.
Okay, another question is which are the main differences with the technology developed by Boston Metals?
Yes, we follow Boston Metal. We at ArcelorMittal we have also some activities with this approach of high temperature. It's very interesting because it's a process that proposed to produce steel in one step, a radical change. But Siderwin is a process that operates at lower temperature, and we have the materials to apply to make it feasible. This material exists. The anode, particularly, it's nickel, simply nickel, as it is used in hydrogen production. We have the materials to contain the electrolyte. We have the materials to produce to have good cathode, etc. And this is the main difference. High temperature is difficult because the materials are difficult to devise. Here we are at lower temperature and we have available materials to build the process.
Okay, and another, I don't know if we have an estimation how long time we will take to produce 100 kilograms of iron.
The amount of production depends on the current. Typically, in the condition of Siderwin, we operate during 2 days, and then it depends on the surface that we treat during these 2 days. With Siderwin, with the 3 square meter of electrode, we will produce samples of 100 kilos. And if we want to increase, we have to increase the surface to develop the surface in width, in length, and in replication.
Okay, I guess that maybe another answer for industrialization is that at industrial scale we will have to replicate the number of cells to produce more kilograms atoms of iron in parallel. Okay. Another question was related to the oxygen. If we produce oxygen at high concentration, is there any danger of corrosion or even explosions?
Oxygen itself is not explosive. Oxygen is in the air at a high concentration. The 20% of the air is composed of oxygen, and oxygen will be used in the overall process, because oxygen is a way to oxidize. It's a way to mix suspension. It's a way to carry some heat, and it's well integrated in our overall flow sheet.
Okay, I think Jean-Pierre would like to do some additional comment. I don't know if he's next to you.
Yes, can you hear me?
Yes.
Yeah, I forgot to say something important at the very beginning when I spoke, and then we listened to this very good and very clear paper by EDF. And what I wanted to say really is that, there have been about half a dozen conferences and seminars since the beginning of this year dealing with the production of steel based on electricity. And every single seminar before this one was devoted to producing hydrogen and then using the hydrogen to do direct reduction. So it's really very popular technology. But during those meetings, the only people we heard talk were people related to the steel sector. So either steel making people or people building equipment for the steel industry. So today, what I found fantastic in the webinar is that we had people who actually producing electricity, who said, look, this technology is fantastic as far as we electricity producers are concerned. So when you hear people speaking about hydrogen production by electrolysis of water, well, sorry. Then they should bring their own electricity producer with them to be very convincing. Well, they haven't done it yet. So this was done in this seminar. It's good that the electricity people spoke so well, actually. Thank you.
Okay. Another question, I don't know if we have the figure, Hervé, is how does the total energy input compare to the energy used in a blast furnace?
Yes, in terms of energy, it's 31% less than the blast furnace if we compare the same route from iron ore to hot rolled coil. This is the figure that we have checked.
Okay, and well, there are more questions, but maybe as I said before, we will try to recover all the questions, because there are many, and we will try to answer them, and we will produce a document, and probably we will produce a newsletter every few months. So maybe next to this webinar, in the next month, we will produce a newsletter with all these questions that we have submitted today, and we will try to answer all of them. So I don't know if, Hervé, you want to add anything else, or if not, we can close this seminar.
I would like again to thank the panelists for the presentation, and thanks the audience for its interest. And I hope we will organize the webinar for the closure of the project in 2023, and with the final conclusion of the operation of the pilot we have presented to you.
Okay, yes. So as I said before, this webinar has been recorded. So as soon as we edit it a little bit, we will put it on the web, and we will send you a link. And also together we will send all these questions. So I invite you to stay tuned to our web page of the project. We will submit news and more dissemination action, as we have said. Probably another webinar at the end of the project. And in between, you can stay tuned to the news that we produce in the web page. And if you are interested, you can also submit your interest and apply for a special interest group that we have in the web page, and you may receive special information for the project. So thank you again for your assistance to this webinar, and we hope it has been interesting to all of you, and see you soon again. Goodbye.
Goodbye.
Thank you. Goodbye.
Goodbye.